So because you go back and slow it down. All right. Transformations is what we're going to be dealing with in this particular unit. The whole thing is about different kinds of transformations that we're doing. So transformations is an operation that maps or moves one point of an original figure to a new figure, whether it takes it and stretches it out, makes it bigger, shrinks it down, makes it smaller, flips it over, rotates it. There's all kinds of different ones that we're going to do. But it's taking a pre-image. So the first blank is pre-image. And maps those points into what's called the image. Okay, so a pre-image is the original picture. The image is the final answer. Now, why they chose to do it that way and not do image and post-image, I don't know. They just chose to do it this way. It's been done this way since years and years of coordinate geometry has been done this way. Why they chose to do it that way, I don't know. But for example, over here on the left side, you got that picture. You've got a triangle ABC. So we'll do triangle ABC. That's just shorthand. Instead of writing out the word triangle, I drew a picture of one. Triangle ABC is the pre-image. So that's the one on the left. And on the one on the right, you've got the same points, but they have kind of looks like an apostrophe beside of it. That is, we read that A prime, B prime, C prime. That is the image. So triangle A prime, B prime, C prime are the points that have been moved. And we're going to talk about all the different ways to move those and make that happen. A transformation can change the position, orientation, or size of a figure. Okay. Position, left, right, up, down. Orientation, that's the rotation type thing, or a flip, or reflection is what it's called. Or the size, that's a dilation. That's like make it bigger or shrink it down. That's the different things that we're going to do. The first thing we're going to talk about is rigid motion. Okay, rigid motion is probably the one of the earlier transformations that you do in elementary math, and usually it's just done with the first quadrant. We're going to do it in all four quadrants with what we're doing because we can handle that. But in an elementary school setting, maybe fourth grade, you start talking about that first quadrant, and you can do rigid motions in that. And rigid motion is when a transformation preserves the size and shape of a figure. All sides, angles, sides and angles, I guess I should say, sides and angles of the pre-image are congruent, a good geometry word there, congruent to the image. A rigid motion just takes a picture, and it's kind of like this binder clip. A rigid motion would be taking that binder clip and sliding it over here. It's still the same size binder clip, still the same shape binder clip. It looks exactly like the pre-image that was there to begin with. It didn't do anything to it to make it change shape. So non-rigid motion would be taking this binder clip, and if I slid it over and then did that changed its shape, didn't it? So it's not congruent anymore. So rigid motion, everything stays the same size, same, or it looks the same. Angles, measurements are all the same. That's rigid motion. Okay, so that's what we're going to do first. And so that next box, translations. That is the first type of transformation that we're going to deal with. A translation, excuse me, is to vertically or horizontally slide a figure. Vertically or horizontally slide a figure. Okay. You're not turning it, you're not spinning it around, you're not flipping it over, you're just taking it and sliding it to the left or right, up or down, or a little bit of both. That's what a translation is. So coordinate notation for that, the way that works is you have an ordered pair, x comma y, and then they will give you a formula, or we may have to find the formula later on, x plus h, y plus k. You're adding, and if it's a negative move, or you're going to subtract. So h represents the horizontal shift. K represents the vertical shift. Okay, so horizontal shift, vertical shift. Horizontal, X, the X-axis we know on the coordinate plane goes left and right. So if we change X, it's going to change its left and right position. If we change Y, it's going to change its up and down position. Okay, so what we're going to do here is we're going to take a few problems. We might not do every example that's on this page, just because I think you'll get it after the first one or two on most of this stuff. And we're going to translate some figures. So the first figure is number 1. It says rectangle QRST with vertices negative 6, 1 at Q. R is negative 3, 1. S is at 1, negative 5. And T is at negative 2, 7. Okay, so we're going to draw that. The instructions say graph and label each figure and its image under the given translation. So we're going to use 2 different colors. So we're going to graph the original image first. Okay, so I'm going to do QRST. I'm going to do it in a blue pen on the screen so you'll be able to see it real well. And then I'll do the image. The pre-image is going to be blue. The image is going to be red. So the pre-image is just taking these ordered pairs and plotting them. So may have been a minute since you plotted ordered pairs on the coordinate plane. Maybe it hasn't. Okay, so how do we plot the first point, negative 6, negative 1? 1, 2, 3, 4, 5, 6, and down 1. So that is point Q. So we put the letter Q beside of it. And then let's do point R. And up 1. That is point R. Then point S. All right. Down 5. 1, 2, 3, 4, 5. And then point T. Left 2, down 7. And then we're going to draw that rectangle that we get there. So just a straight edge. You don't have to have a ruler because we're not measuring the lengths of those sides. We're just drawing a figure here. So just straight lines if possible, or as best you can. I got a rectangle there, and that is the pre-image for this particular translation. The image, notice underneath there, you've got a boxes to fill in for Q prime, R prime, S prime, and T prime. So we're going to write down the ordered pairs of our image. These are the rules. That's the rule we're following. X plus 5 and Y plus 7. We do exactly that. So if I add positive 5 to negative 6, negative 1. If I add 7 to negative 1, I get positive 6. So I know where Q prime is going to be is at -1, +6. And I'll put Q prime there. I did. All right, so I'm adding 5 to the x value of Q. So -6 plus 5 is -1. And then I'm adding 7 to the y value for Q. So -1 plus 7 is where the 6 came from. And I'm going to go plot that point. So -1 up to 6. 1, 2, 3, 4, 5, 6. And Q prime. So just labeling that point. And then do the same thing to R to get R prime. So -3 plus 5 is 2. And 1 plus 7 is 8. So, or that's R, not S. I went left instead of right. So 2, 8. And for 2, 8. 1, 2, 3, 4, 5, 6, 7, 8. That's R prime. And then S prime, taking S and doing the same transformation or translation on that. 1 plus 5 is 6. -5 plus 7 is 2. 6. 1, 2, 3, 4, 5, 6. 2. S prime. And T prime, -2, 7. Add 5 to -2. Get 3. Add 7 to -7, and what do you get? 0. 3, 0. Right there. Good old T prime. And you draw that new rectangle that you got there. If it doesn't look like a rectangle, something went wrong when you were plotting your points. It should look exactly the same. Remember, we're doing rigid motion here. We're not changing the shape of that or the size of it. They should look like they're the exact same size, just picked up and slid up there. Probably the easiest thing we'll do today. Well, maybe not. That's pretty easy, but it may not be the easiest thing we do today. Hey, y'all feel pretty good about that? Do we need to do number 2? I'll be glad to do it if you want to. All right, pretty easy thing. Just follow the instructions on the rule. That's what we're doing. Okay. 3 and 4 is the same idea. We have a rhombus. Let's just discuss the shape. What's a rhombus? Kind of like a crooked square. It's like as one of my students says, it's a square that got hit by a bus. It's just all the sides are the same length, but it doesn't have the 90-degree angles like a square does. So rhombus is that shape. Still the same rules here, following the transformation or translation that it's giving you. And then number 4 is a square. You know what that looks like. So, but just following the rules. What about the rule on number 5? What is the only kind of motion that they're doing there? Yeah, so they're shifting it which way? Yeah, to the left 7, or to the left 7 on that. And they're not moving it up or down at all because the Y stayed the same in the rule. So just follow the rules. If they don't do anything to the Y, all the Y values stay the same, and it makes it even easier, like it wasn't easy enough already. So y'all got that. That's easy. All right, now there's a little tougher part. And this is where you actually have the pre-image and the image drawn on the graph. So flip over to the skip. When on your notes there, the part that says vectors, exit out. The part that says translating with writing vectors, exit out. And get down there to number 15 and 16. And we're only going to do A part. So mark out B part there. We're not doing B part. Vectors is not something that you will get into in elementary school math or K through 8 math. If you get into vectors in that area of mathematics, then you've got some awesome kids, and you better hang on because they're going to be smarter than you. They will be smarter than me too, because we don't do vectors at Adamsville High School until they get into pre-cal. Just that's not a standard that's tested in geometry, so we don't do it in our geometry classes. But it is something we do in our pre-cal classes with vectors, which is a neat thing. Gets into physics and all that fun stuff. It's really cool stuff. So we're going to write a rule in the coordinate notation. So what we're going to do is we're going to write a rule like our problems had here. We're going to write something like that. That's what we're going to do with these problems. Okay, so this is a little higher level. It's that synthesis. I can't say synthesis level of Bloom's taxonomy. Does Dr. Swan still talk about Bloom's any? And it's still a great theory of education. So Bloom's and the taxonomy of the synthesis and creating the equations that come with this, or the rule for that. So how did we move D to D prime? Okay, so the best thing to do is find out, okay, well, what's point D? What's the ordered pair for point D? -3, +3, right? And then D prime, 1, 2, 3, 4, 7. All right, so how in the world do we get from a -3 up to a +4? Add 7. And how did we get from a 3 to a 7 on the y's? Add 4. And we got the rule. Check it with point E and point F if you want to. It works. All you really have to do is use one ordered pair. The rule's the same for all of those because you're not changing the shape of it. If you were doing some sort of dilation there, then yes, there's some other things that happen. But here we're just doing rigid motion. So we're just taking one picture and moving it around, just picking it up and sliding it in a Ouija board fashion. All right. Let's do 16. Let's go ahead and do it. So I need to get two ordered pairs. Y'all pick one to start to use. Those are that's the prime, that or M prime, N prime. Those are the image. That's the finished result. That's the one you get to. So which point do y'all want to use? M's fine. So what is the ordered pair for M? 3, -3. That's boring. What's M prime? -1, 8. Well, let's see. Well, what's it in the picture? That's what matters. And it would matter when you go to write your rule, because if you're moving from M to M prime, it's a different rule than moving from M prime backwards to M. And so it would be that's the opposite sign there. So yeah, it does matter. All right, so how did we get from 3 to -1? Subtract 4, good. And then from -3 to -1, adding 2. And you can check that rule with one of your other points. If you check it with N is at 1, 2, 3, 4, 5, 6, 7, or no, 6, -4. So 6 minus 4 would be 2. N prime is at 2. And then -4 plus 2 is -2. That's at -2. So yeah, N prime works as well. So checking that rule that you're writing, okay? So we're marking out the vector part and just doing the rule out of that, just because vectors is not a K-8 standard at all. If you go somewhere where they're wanting you to teach vectors in elementary school, you're not in a public school. but it's not a hard concept. It's doable. All right, so the next thing, flip over there to the next page. We talk about reflections and flips, or what reflections are. A flip is what my sons like to do off the couch over a line. They call it the finish line. We call it the line of reflection. Okay, so we're going to be flipping some figures across that. So this is not not a rigid motion because you're changing the orientation of the figure. It's flipping it over so it looks different. It's the same size, but the orientation is different. So it's moving away from that rigid motion idea. Each point and its image are the same distance from the line of reflection. So whatever our line of reflection is, if a point is 2.2 blocks away from it on the image or the pre-image, the image is going to be 2 blocks away from it on the other side in the final result there. So it's rigid in the fact that it keeps the same size and basic shape. It does change the orientation. So put in there changes orientation. So we we keep the same size though. So keeping the same size, I guess technically makes it rigid in my definition of rigid motion in the way that you no deeper than you get into it in elementary school. The changing the orientation kind of can make it weird. All right, common lines of reflection. A lot of times we'll reflect across the x-axis or across the y-axis. That is very, very common, and we'll do that the biggest part of what we're doing. And then we can take that same idea and reflect across horizontal lines or vertical lines. The vertical lines are x equals some number, and the horizontal lines are y equals some number. It's a very easy concept to do because we're just dealing with distance a point is away from the line of reflection. You're not really having to do a whole lot of calculations involved here. Diagonal lines are also something that we could reflect across. I think you can rest assured that you're not going to get any more complex diagonal lines than those two to reflect across in Math 192 for sure. In maybe an algebra class, you might get into reflecting across some other fancier slope-intercept form line, but we're not going to do anything fancy like that. We're just looking for basic idea of reflection across that. So when we reflect across the x-axis, so which axis is the x-axis? One goes this way, okay? So what happens to the ordered pairs if I have one that's up here above the x-axis and I reflect across it? What turns negative? Does the x change if I just reflect across the x-axis? It just flips down. The y changes signs. So when we flip across the x-axis, the y is going to change signs. When we flip across the y-axis, what's going to change signs? The y-axis is this one. So if I start over here, if I reflect across it, I'm going to go the same distance on the other side, right? So that's just going to change the sign of the x value. The y value is going to stay the same. So when we're reflecting across the x-axis, our y value changes signs. Reflecting across the y-axis, our x value changes signs. So maybe that's something you probably want to jot down somewhere. It'd be a good idea. We're going to do a couple of reflections here. We'll do a reflection across the x and the y-axis with these number 1 and number 2 there. So triangle ABC has these vertices, corners at A being -4, 2, B being 4.7, and C being 5.1. And we want to reflect across the x-axis. So again, I'm going to do the image or the pre-image in blue and the image in red, just like I did on the other one. So plotting points, A is going to be at -4, 2. B is at 4.7. And C is at 5.1. And then I'm just going to draw that triangle. I said it was. ID badges are not cooperating. You're no longer an ID badge. You are a ruler. Okay. And underneath there, you got a nice little place to write the ordered pairs for your image. So again, reflecting across the x-axis. So this is the line we're reflecting across. And I'll draw it maybe in orange. Can you see that? Yeah, good. So that's the line we're reflecting across. And we know A prime should be 2 units below the reflection line now instead of 2 units above. So there's A prime. What's that ordered pair? -4, -2. And then B prime, what would be the ordered pair for that? 4, -7. And let's go ahead and get the ordered pair for C prime. 5, -1. Yeah. B prime. And draw your pictures. And we've maintained the size and shape, but the orientation is different in that reflection across that x-axis. Notice how they're all the same distance away from that. If you were to fold that picture across the line of reflection, they should match up perfectly. Nothing too exciting about this. This is not blow your mind kind of math. But it is fun. One of our art teachers does some projects with reflections and tries to get kids to create some artwork doing reflections and rotations and things. Tessellations is I think the art term for that. I did a research project on that in my undergrad. It was quite fun, called freeze groups. So the theory behind all of the mosaic tile that you see, that's the same pattern, just rotated in different order. It's really pretty when you put it in tile work. But the math behind it is not as easy as it sounds. It's easy when you do it with tile, but it isn't so easy to do it on paper. So, but it's a neat thing. But it all stems back to these transformations that we're doing here. All right, so let's do number 2. It's a reflection across the y-axis, just so that we can say that we've done that. So I'm going to plot PQRS in blue. So P is at 1.2. Q is at 2.5. R is at 8.3. And S is at 7.0. We get a rectangle. Nice looking rectangle. We are reflecting across the y-axis. So we know the shortcut is that what changes? The x value changes to the opposite sign. So P prime should be at -1, 2. But we also understand that it should be equidistant away from the line of reflection. So it should be 1 unit to the left instead of 1 unit to the right. Q should be 2 units to the left, or Q prime should be. But we know that that's actually just -2, 5. R prime should be same y value, and then S prime, same y value, negative 7.0, and that was R was negative 8.3. And we get that nice looking rectangular shape that's the same size as our blue one. Nice, beautiful reflection across that. The more intricate your shape, the cooler looking your reflection looks. Awesome. All right. 3 and 4, same ideas. X and Y axis, I don't see a need to go over that again with that. But let's go over to the next page to 5 and 6 and talk about reflecting over a different horizontal line and how we don't have the shortcut quite as easily for that as we do with the x-axis. So we are going to take this image of triangle JKL and we're going to reflect it across the line x equals 4. So x equals 4 is this line right here. So I just went to 4 on the x-axis and made a vertical line. And that's my line of reflection now. And do what now? Yeah, I would go ahead and draw that line in some different color than what you're using to do your image and your pre-image and image, just so that you can reference to that when we're doing that. So let's go ahead and plot the image or the pre-image. Excuse me. J is at -1, -1. K is at 2, 3. And L is at 3, -2. I didn't do that right. 3, -2s right there. And we got this triangle. And we're going to reflect it across that line. So I always usually just start with the point that's closest to the reflection line because it's easier to get that starting point there. How far away is point L from the line of reflection? Point L, yeah. It's 1 unit away. So I'm just going to pop, and I wrote that in red instead of blue because I was doing my images, pre-images in blue. Now, there we go. So L is going to flop over that line, and there's going to be L prime. That ordered pair is 1, 2, 3, 4, 5. Then the Y value is the same as L, which was -2. That's the same distance away from the line of reflection. J is how many units away from that line of reflection? 3. So I'm going to go up here to J prime. It's going to be there. So that's going to be at 6, 7. And then the same Y value. And then K prime is 2 away. So that's going to be 5, 6. And the same 6, 3. I didn't do a good job drawing that. Lines are not. That's better. And we get that reflection across that. Not as nice as far as shortcut on the ordered pairs. There are some shortcuts on there. My high school geometry kids, I make them figure it out and learn the shortcuts on it just because I want them to think a little bit more in lines of speeding up for ACT purposes. You guys, we're not trying to speed up for ACT purposes. I think it's more important with what we're trying to learn as far as the context of where we're going into the primary school classroom, the distance away from that line of reflection is what you want to emphasize, not necessarily the emphasis on learning the shortcuts on the ordered pairs out of that. If a kid, if I'm teaching the seventh, eighth grade with this, then maybe talk about that there. But if I'm doing translations or transformations with fifth and sixth graders, I'm probably talking about, okay, make sure your distances are the same and use it in that context. So age of appropriateness for shortcuts and things like that. Number 6 is also a reflection across a vertical line. So I'm not going to do that one unless you guys want me to, and I'll be glad to if you want it. You just say, don't feel bad. Yeah, just the x equals -1. Your line of reflection is going to be not crooked like that one is, but x equals -1 is going to be that line right there. So you go to whatever the x-axis number is. Yeah, we're going to do that with number 7 and 8 there. So which one would y'all rather do, 7 or 8? 7 with a parallelogram. I like the parallelogram. They're fun. All right, so parallelogram. It says we're going to reflect this parallelogram CDEF across the line y equals 2. So my reflection line, I'm going to go on the y-axis to 2, which is right there, and that's going to be my horizontal line that I'm going to reflect across, is that line right there. Mm-hmm. Do you want us to draw that line? Yeah, go ahead and draw that line of reflection, especially if it's not one of the axes. Of course, the axes are already drawn there for you, but if it's a different line, draw that reflection line on it. That's a good reference for me and for you on that to do. So plotting our pre-image, C is at -4, -4. D is at -2, 0. E is at 6, 1. And F is at 4, -3. Did I do that right? I miscounted on my C. My eyes are a little bit tired today. And because it wasn't looking like a parallelogram, that's how I knew that. 2 sets of parallel sides on the parallelogram. Rectangle got hit by a bus. And then we're going to reflect that across that horizontal line there. So our I again go to the point that's closest to the reflection line and start there. That's not a rule that you have to follow, but it's just my way of doing it. I think it's easier. So I go to E. It's 1 unit below, so E prime should be 1 unit above. So that is at the point 6, 3. And then D prime is 2 units below, or D is at 2 units below, so D prime would be 2 units above. So it's same X value. Y value is 4. Yes. Yes, you do need to put the letters beside the dots when you graph them. That way I know which ones they are. Sometimes you're going to get an image where you got 2 points that line up on the same, are vertical of one another or horizontal of one another, and it's easy to get them swapped the wrong way. So you got to make sure you're doing it right. C prime is 1, 2, 3, 4, 5, 6 units below. So 1, 2, 3, 4, 5, 6 units above C prime. So same X value, Y value is 8 this time. And then F prime should be 5 units above. So that's going to be at 4, 7. All that reflected parallelogram. Super cool. But easy to do. I don't focus on the shortcuts on the ordered pairs, especially when I'm reflecting across a different line, just because it doesn't tend to help us real, a whole lot out of that. It's actually quicker to just count. So do it that way. All right. All right. So let's go to the next little piece there at the bottom of your page. You've got reflecting across y equals x and y equals negative x. So if you don't remember from a good old Algebra 1 class, and I'm going to kind of try to fix mine is not kind of squished a little bit when I copied it over. So we're going to reflect that across the y equals x line for number 9. The y equals x line is a diagonal line that just goes from corner to corner. And I better get a straight edge so it looks right. I'll have a little longer one this time. So it's going to go through the origin, and then it goes up 1 and over 1 the whole way. Like that. So there's our line of reflection. The y equals x line. That's what that is. Y equals x. I'm going to reflect across that line. And so I'm gonna plot my pre-image, -5, -2. There's x. Y is at -3, 4. Y. Z is at -1, 1. And there I've got my pre-image that I'm going to try to reflect across that line. So distance is a little tougher on the diagonal than it is on the vertical or horizontal. You've got to think about, okay, we've got a diagonal distance out of this or slanted distance. So it's not about measuring with a ruler. Don't think that you're going to do it that way, because that's not necessary. So I'm drawing that triangle. Tired of messing with it. All right, so when you look at the points, if I look at point X, I'm going to count from this spot. I'm going to count that kind of L shape. The reason I'm going to do that is that what that does is it creates a right triangle. And you guys remember Pythagorean theorem that works for that. But it really doesn't matter what that length of that diagonal is. We just know that it needs to reflect that shape going the other side. Okay, so we need to go this far. So that would be a down 1 over 1. Or backwards. Over 1, down 1. Same place though. And that's going to be x prime. So x prime. Over 2. I'm sorry, I did miscounted there. Yeah, flip it over there. So our ordered pair should be at -2, -5. 1, 2, 3, 4, 5. Over 2, down 1. Flips it over. Instead of you flip over the reflection. Okay. This length is over 1, up 2 to get there. We're going to go the opposite direction there. We're going to go over 2, down 1. And that's going to give us the same length away. Same distance away. Did I miscount? Down 2, 1, 2, 3, 4, 5. That's x prime. Oops. Pasted my reflection line. 1 over 1. Z should be at 1, -1. Because that one's only 1 unit away both ways, so it doesn't matter. If you flip it, it's the same because it's 1 and 1. So Z prime should be here. It should be 1, -1. Y, we got to go. So we're going say that again. Swap it around. Should be 4, -3. Waste my point. Next. Same distance away on both sides. And you're counting it and turn it, go the other direction. 1, 2, 3, 4, 5, 6, 7. Let's try number 10. Let's go ahead and do that. Same reflection line, because these are tougher. Notice what it's doing to the ordered pairs. I miscounted on my Y. And so I put that at 5 instead of 4. Not opposite, but swapped order. That's what you mean. That's what happens. When you reflect across Y equals X, it just swaps the order of the ordered pair. X, original X was -5, -2. X prime, flip it around, -2, -5. Original Y was at -3, 4. New Y prime is flip it around, 4, -3. When you're reflecting across Y equals X, yes. That's the ordered pair shortcut. You see what I'm saying? Yeah, it does make it a lot easier if you do the shortcut with the ordered pairs. But again, emphasis on the distance away from the reflection line. So G, 2, -1. H is at 7, -1. I is at 7, -4. And J is at 2, -4. Get the rectangle. We're going to reflect it across that Y equals X line. It should be at -1, 2, right? For G prime. Wrote the order pairing off -1, 2. G prime. H prime should be at -1, 7. Should be there. And then J prime should be at -4, 2. I prime. Oh, I wrote the J prime and I prime part. I prime should be at -4. So, and there we got the old reflected rectangle. Count, count, count. And reflecting across y equals x. Go swap your ordered pair around. That's what it does out of that. Reflecting across y equals -x is the next thing. So 11 and 12. So reflecting across y equals -x, the line that's the reflection line goes from top left to bottom right. Like that. That's y equals -x. That's our reflection line that we're crossing. Flip and change the sign of the x. Okay, so or flip and change their signs, like both of them. So -1, 3 is A, so I'm gonna plot that -1, 3, and A prime would be at flip it, change the sign, -3, 1. See how those are equidistant away from the reflection line? So C or B is at 0, 6. B prime would be at -6, 0. And 0 doesn't change signs, so -6, 0. Not 0, -6. And then C is at 3, 5. Yep. D prime or D is at 2, 2. So D prime would be at -2, -2. So flip and change or swap and change the signs. When you're reflecting across y equals x, you just swap. Y equals -x, you swap and change the sign of both. There's a shortcut to that. And look at your picture to make sure it looks right. Not too difficult. That's the reflecting across y equals x and y equals -x is the toughest ones of the reflections as far as that goes. But again, y equals x, you swap x and y. Y equals -x, you're going to swap and change the sign of both. Make them negative or opposite of what they are. So swap and change signs. So swap, change signs. Y equals x. Just swap. All right, the next piece about identifying the line of reflection. I think this is not terribly difficult. Number 13, what would be our line of reflection there? X equals 0 or the y-axis. X equals 0 is this line right here, but that's also the y-axis. So 14's a little harder. Y equals negative x. Yeah, so if you do that line through there, you can see that y equals negative x. Do what now? We'll call it what? Do you remember this from college algebra or yeah, slope-intercept form? For these, the slope is -1 and the y-intercept is 0. So it starts at 0, 0 and goes down 1 over 1 the whole way. That's the slope. That's the y equals negative x line. Has that slope of -1. So whatever x is, the y value is -1 times that x. That's what that line represents. And it's just a line diagonal down and to the right. Is basically all you got to remember about that. It's nothing. Like I said, most of what you're going to encounter in the younger elementary grades are going to be reflecting across the x-axis or the y-axis. With when you get into junior high, that's when they start doing that slope-intercept form and all that stuff. So 7th and 8th grade math. So you folks that get middle school certified, you could end up having to do that with the y equals x and y equals negative x. What about 15? Not y equals -3 would be this, would be that. Okay, x equals -3 because it's a vertical line. And you could see if you drew that line through there, how the reflection happens. 16's tough because it's on top of one another. Y equals 0 or the x-axis. X-axis is what I would, on the other one I'd say y-axis instead of those other equations. Because it's, I guess, a stronger thing because it's a special axis. 17. Y equals 1. And if you look at the z values, the y values on the z's, -2 and then +4. What's halfway between those? Y equals 1. And then number 18. Yeah, y equals x. Again, it's whatever x is, y is the same thing. And that's that reflection line. You can kind of get, eyeball these and see where they're happening, what the reflection, if it's going to be the axis or that y equals x line or something like that. Okay. All right. The next thing we're going to talk about is rotations. And a rotation is when you turn a figure. So we're going to turn around a fixed point called the center of rotation. You hear them talk about this when the storms and things are coming around or the low pressure fronts coming in. They'll talk about the center of rotation for the fronts and all that stuff. All relates back to the geometry that's happening with the weather map and the radar and all that fun stuff. So we're going to center our rotations around the origin, and the figure is going to rotate at a specific angle and direction. There are constructions that you can do that we hopefully we'll have a day where we can just do constructions at the end there and learn to do this. But you can take a figure and say this rectangle here, and you can rotate it, say 30 degrees clockwise. So clockwise would be when you're facing it would be this way, right? And or for you guys, clockwise would be this way. So when I rotate this clockwise 30 degrees, it's going to move it about like that. If I started here and I rotated counterclockwise 30 degrees, that'd rotate it that way, 30 degrees. And you can do constructions to do that, and it takes a compass and a protractor and measuring that angle and all that fun stuff. What we're going to do is take specific common rotations that we're dealing with. We're going to center them around the origin instead of around a different point. It's a lot more involved when you center it around a different point and you rotate a different degree amount. So we're going to rotate 90 degrees, 180 degrees, and 270 degrees. The rotations that we're going to do in the original format are going to be counterclockwise rotations. That's the common way of doing things in math is counterclockwise. So a 90-degree counterclockwise rotation is like a translation, but it changes the orientation of the thing and swaps the X and Y and changes the sign of the Y. Oh, origin. I said it and didn't write it in there. Sorry. We're going to center everything. We're going to center around the origin. It's the most common point of rotation. On a clock face, the center of the clock, the origin basically, is what we're dealing with here. So we're going to rotate an object 90 degrees counterclockwise about the origin. This is what it does to the vertices. It swaps the X and Y and then changes the sign of the Y. So we're going to learn, you're going to do a memorized ordered pair transformation on this instead of doing the actual angle measurements and the compass and getting it exact the right spot. We'll talk about that maybe that last day before the final or something like that. 180-degree rotation. Notice it doesn't say clockwise or counterclockwise underneath that, because what happens when you go 180? It's if you go clockwise or counterclockwise, in the same spot, right? So it doesn't matter which direction you're going to go there. And what the 180-degree rotation does is it just negates the X and negates the Y. Changes their signs. That's all it does. Doesn't swap the order, just changes the sign. Okay. Rotating around 270 degrees counterclockwise takes the X and Y values and swaps them and changes the sign of the X. Takes the image or the pre-image and the image, swaps the X and Y values, changes the sign of the X. And that's a 270-degree counterclockwise spin. Those are common rotations that happen. You can find the ordered pairs for any degree amount you want, but it is a much more complex construction process, more so than it is a nice, pretty thing that happens. And we'll talk about that maybe later on. So the constructions idea is kind of dying out in geometry for some reason. It used to be that's how you did geometry. Now it's gone to, I guess it's because it's pretty hard to test that. That's my theory on it. It's very hard to test constructions because you can't make that multiple choice format. Drawing a construction can't be done multiple choice wise. So that's my theory on why it's dying out. But I'm a cynic on the testing anyway. So all right, examples. Let's do a 90-degree counterclockwise rotation on a triangle ABC. So I'm going to put my image or pre-image A at 2.7, B at 6.5, and C at 4.1. And I'm going to draw that. I miscounted on my B again. My eyes are not doing too well. Too much. That's pretty good. All right. So we're going to rotate that image 90 degrees counterclockwise. So what it does to the ordered pairs, 90 degrees counterclockwise, swaps the X and Y, changes the sign of the Y. So A prime, instead of being at 2, 7, A prime, swap them and change the sign of the Y. So that's going to be negative 7, 2. B prime should be at negative 5, 6. C prime should be at negative 1, 4. We'll plot those points. And then negative 1, 4. And negative 5, 1, 2, 2. And we see that rotation happening. And if you think about taking your paper and the original image is here and you rotate it 90 degrees counterclockwise, then that looks like that picture that's on the left in red. So rotation 90 degrees counterclockwise. Rotation 180 degrees does what to the ordered pairs? Changes the sign of X and Y. I think you guys can do that. I think we need to draw that out. Number 3, 270 degrees counterclockwise does what to the ordered pairs? Yeah, flip them around, swap them over, change the sign of that original X value to the opposite, and that gets you that. A 270 degree counterclockwise rotation would be the same as how much clockwise rotation? 90. A 90 degree counterclockwise would be the same as how much clockwise? 70. An idea. So those are important things. I think you guys can follow the instruction on the ordered pair thing. I don't think we need to waste more time doing that. You guys are smart. You can do that stuff. So let's flip on over to get to the page that says rotations again around other fixed points. Mark that page out. And the next page. The page, we're skipping all the way from where we were at to, past the clockwise examples. No, mark them out. You're still going to have to do them. We're just not doing them together because you guys can follow the instructions on the ordered pairs. So go get rotations about other points. Mark that out. We're not doing that. On the next page, numbers 2 through 5, mark all of those out. We're not doing that. That involves vectors, and we're not doing vectors. And get to the page about dilations. Dilations. So looking for the page about dilations. We're doing that. On the homework, I'll tell you which problems to mark out, okay? So that maybe that'll narrow it down here. So going to the dilations page. Oops. Dilation. All right, a dilation. Not a dilation, but a dilation is an enlargement or reduction of a figure with respect to a fixed point called the center of dilation. A dilation is an example of a non-rigid motion because it does not preserve congruency. It's not the same size anymore. Dilating something, get bigger or smaller. Okay, it's not the same size anymore. Dilations produce similar figures. And that is a topic we'll get into after spring break. We'll get into things about similar figures and do some work with those things. So pretty easy thing though. All corresponding angles are congruent, and all corresponding sides are proportional. So the proportional part of that, the angles are the same though. So the general shape of it, if it's a triangle and you dilate it, it better look like a triangle, just the same one, bigger or smaller. It's just shrinking and stretching. That idea is what we're going to do with this. So a scale factor indicates how much the figure will be enlarged or reduced. Okay. The variable for the scale factor that we tend to use is the letter K for no apparent reason. Okay. But that's the accepted way for mathematicians to use the letter K when we're talking about a scale factor for our dilation. Okay. When K is greater than 1, the dilation is an enlargement. When K is less than 1, the dilation is a reduction. Okay. Your scale factor, think about it when, I don't know if anybody uses Google Earth anymore, but when you used to use Google Earth, you could change the scale by, now you do it on your phone instead of the computer, but you change the scale by pinching in or pinching out. So that's what we're doing here, changing the scale by pinching in or pinching out. If we're making it larger, it's like pinching in. The K has got to be bigger than 1, so we're making it bigger by multiplying by what kind of numbers are greater than 1? Positive, bigger numbers, right? Like positive 2, positive 4, positive 162, those things. And then numbers that are less than 1 are dilations. Now, here's a thing here. By saying K is less than 1, that is got to be a fraction, okay? Not necessarily a negative number. Because a negative multiplying by a negative doesn't necessarily dilate it. It may change its orientation. But this should also be, make a note that that's a fraction or decimal. That's how it reduces in size. Not that it's a reduction doesn't necessarily happen, because if you multiplied by -3, it would kind of implode on itself. That's kind of turning it inside out. That's a whole geometric thing that's weird that happens. But our K value, what happens is we take an ordered pair, and when we're dealing with a dilation centered around the origin, and that's how we're going to do things. We're not going to do centered around a different point. When we're centered around the origin, the scale factor will follow this transformation rule. It will multiply times x, and it will multiply times y. Whatever your x value was, multiply it by the scale factor. Whatever your y value was, multiply it by the scale factor. That gets you your image ordered pair. It's a really simple process. Nothing too exciting about this. When you're centered around the origin, if you're centered around a different point, it kind of changes things a little bit, depending on what the orientation of that point is to your particular figure that you're dealing with. So we're going to do a couple of examples here. We'll do an example of an enlargement and an example of a reduction. So in enlargement, what does K have to be? Bigger than 1. So example 1 or example 2 are both enlargements because K is 2 and K is 3. So I'm just going to do example 1 with an enlargement. And I'm going to, again, graph the pre-image in blue and the image in red. So triangle RST, R is at -5, 1. where R should be. S is at negative 3, 4. T is at 2, negative 1. Again, I'm drawing that figure, triangle RST. The dilation that is happening is multiplying by 2. So the point R prime should be at negative 10, 2. So you multiply negative 5 times 2. That gets you the new X value for R prime. Multiply the Y value by 2. That gets you the new Y value for R prime. So negative 10, 2. S prime would be at negative 6, 8. And T prime would be at 4, 2. Or 4, negative 2, excuse me. And then we're going to plot those points. 2, 3, 4, 5, 6, 7, 8, 9, 10. R prime. And then negative 6, 8. S prime. And then T prime. Should see the same shape, just stretched out. It kind of can look weird sometimes until you get the figure drawn. And it's just stretching it out there, and you get a point it ends up crossing over there sometimes. So dilation multiplying by the scale factor. That's all you're really doing. Very, very simple process. Let's do number 3. Take a rhombus, and it says dilate that with a scale factor of 1/2. So that's going to reduce our picture and go from there. So I'm going to stretch out my picture here. We'll just put it that way. All right, so image JKLM, negative 10, 2. J, K is negative 2, 8. L, 6, 2. And then M is negative 2, negative 4. Rhombus, it's a square been hit by a bus. And then the scale factor is 1/2. So what's that going to do to everything? Divide it by 2, right? So that's going to be 5, 1. K is going to be at negative 1, 4. K prime anyway. L prime would be at 3, 1. And M prime would be at negative 1, negative 2. M 3, 1. And there we have the that's, you get the idea. So dilations enlarge or reduce by multiplying the ordered pairs by the scale factor that's given. Okay. Questions about that part? Pretty easy stuff, right? The easy things to get done before spring break, right? All right, let's look at number 11 there. So flip over till you find number 11. Well, I skipped it there. Let me scoot back up here. It says A prime, so it's a kind of a word problem idea. So no picture on this one. It says A prime is the image of A after a dilation centered at the origin with a scale factor of 2. So A prime, you got to remember, is the image. We want what the coordinates of the pre-image were. So what are the ordered pair for A? -5, -4. Good job. What about number 12? This is a little tougher one here because we've got a scale factor of 1/3. We have the image point, -2, 5. That's after a dilation centered at the origin with a scale factor of a 1/3. What are the coordinates for P? -6, 15. Good job. The opposite of multiplying by 1/3 would be multiplying by 3, the reciprocal of that. So the undo that is a reciprocal. Is number 13 an enlargement or a reduction? Why? Yeah. It's ended up 1.5, so it's bigger than 1. So that is an enlargement out of that. So the same idea though. If you wanted to get the image, you've got the image, you want the pre-image ordered pair. What is the pre-image ordered pair for Z? What do I multiply 3 by to undo the enlargement? How did we do it for 12? We multiplied by 3, the reciprocal. What's the reciprocal of 3/2? 2/3. So it would have been 2. 8 times 2/3. 16/3. Multiplying by the reciprocal is the same thing as doing what? Yeah, dividing by the fraction that you already have, or the number you already have. So multiplying by the reciprocal is the same thing as dividing by the number you have. On number 11, that's what we did. We just divided by 2. That's the same thing as multiplying by the reciprocal. When you get the fractions in there, that's where you got to think about that happening there. So be careful of that. Go down to 15, that picture at the bottom. Identify the scale factor given in this the image and pre-image of these things there. So how could we do that? Okay, so pick me an ordered pair to work with. Which one do you want to do with? D, E, or F? D's fine. All right, so point D, what's the ordered pair for point D? 0, 6, and D prime, 0, 2. How did we get from 6 to 2? Divide by 3, which is the same as multiplying by 1/3. So our scale factor is going to be 1/3. Got to remember that D prime is your final answer part, and original D there is the pre-image. So be careful of that. Multiplying by 1/3. So, and your scale factor's always got to be a multiplier. So when you say, okay, I divided by 3, think, oh, it means I multiplied by the reciprocal of that. That's what you want to think about. What about number 16? Same idea, just it's a different type of problem here. W is fine. So W, the ordered pair for W would be -2, 2, and W prime -8, 8. So how did we get from the pre-image to the image? Yeah, we quadrupled everything, multiplied by 4 to get there. Again, it's from pre-image to image that you're going out of that. All right. The next page says dilations from other fixed points. Mark that page out. We're not doing that. The next page is more problems with dilations of fixed points. Mark that page out. We're not doing it. The next page is identifying the center of dilation. We're not doing that. Mark that page out. I killed some trees today with some papers we didn't need. Sequences of transformations. That's the next place you want to be. Sequences of transformations. Basically, when 2 or more transformations are combined to form a transformation. So what happens when you take triangle XYZ with those particular ordered pairs and A reflected in the x-axis and B translated along the rule x plus 9 and y plus 2. So let's think our way through this. What happens when you reflect across the x-axis to the ordered pair? Yeah, Casey got the right idea. It does this. So -3, 7, somewhere up here, right? And it's going to move down here. And then the translation does what to that new ordered pair? Slides it to the right 9 and back up 2, right? So our image is going to be somewhere up here, and then our final image, the pre-image is going to be somewhere up here. Our image is going to end up somewhere probably down here. So we're just going to apply both of these transformations to the original pre-image. You can do them one at a time, or you can do them at once. If you can think your way through just doing it, I think it helps to draw both of them. And then the last one be, the middle step, just kind of make it ghosted, like dotted lines or something like that. And so let's just do this one together here, and we'll see what we can do here. So I'm going to do as in the past, I'm going to do my pre-image in blue. So I'm going to go to -3, 7. And that's point X. And Y is at -2, 1. And Z is at -5, 2. And I'm going to draw that image. Or that pre-image. And then the first transformation that happened to A there, you just do it in the order they give it to you. So they gave us a reflection in the x-axis. So that's going to flip all that stuff down to the bottom. So Z is going to be here, right? Just swap that to, in between. So A gives us Z at -5, -2, and Y at -2, -1, and X at -3, -7. And then B part's going to be the final answer. So I'm just going to kind of put those points there. And excuse me. And draw this little ghost figure here. This isn't the answer. That's just where we're at to start off, to do the next transformation. Okay. And I've just made a note of what those are going to be. And then the next transformation they said is, okay, slide it to the right 9 and up 2 by adding 9 to the x's and adding 2 to the y's. So add 9 to 5. 9 to 5. Dun, 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 dun. It'd be 4. And then add 2 to y. So it'd be 0. And then do that for, that's the wrong point. That's z. 4, 0. And then x would be 6, -5. Y would be -2 plus 9 is 7. And then -1 plus 2 is 1. So then I would plot those points as the image, x prime, y prime, and z prime. So, yes. Don't go back to the originals. Go back to the previous step to do your next transformation from. Okay. So 6, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. There's x prime. 7, 1. Y prime. 4, 0. Yes, that's right. That's right. You don't have to draw the middleman there unless you want to. When you go to explain that, so like on maybe the final exam or something, they ask you to explain the process of doing multiple transformations. You would somewhere in there say, after the first one, these are my ordered pairs, and then there would be an image in between, or something like that. You don't necessarily have to draw that image though. So it works out real nice for that. Number 2, you're doing the same thing. You get translate it, or number 2, mark out. It's got a vector in it. We're not doing the vectors. Sorry. Mark out number 2. Mark out number 3. Number 4. Same idea. But you got to reflect it across the y equals x line. Number 4. Yeah. Number 4 doesn't do vectors. It just does the reflection across the y equals x line and then a translation along that rule. So again, get your in between on a part and use those to follow the translation rule there. Not anything terribly difficult there. Number 5, you got a rotation of 180 degrees. What's the rotation do to the ordered pairs of the pre-image? Does it swap x and y? Keeps the same x and y and changes the sign, right? Change the sign of both of them. So if you go back to that 180 there, just change the sign of both of them. Doesn't swap x and y, just changes the sign of both of them. Yeah. Okay. Okay. All right. That'll be fine. That will be fine. And we'll tell her which ones are omitted and all that stuff. No problem. Okay. Where were we? We're here. What page we're on? All right. We did skip those. All right. Skip over. Thank you. Just like okay. Okay. And then yeah, and I'll post it on Canvas which ones they'll be at again, just in case we don't communicate well when we get to that point. Yeah. All right. Now skip over to the last thing of the day. We're almost done. Symmetry. I like symmetry. Symmetry is a wonderful thing. There are several types of symmetry. 3 that we're going to focus on: line symmetry, point symmetry, and rotational symmetry are what we're going to talk about. Okay. Line symmetry is just that. You can draw a line through it and fold it along that line, and it matches up perfectly. Okay. So, for example, this triangle would have line symmetry down that little. If you drew that line right there, it's line symmetry. Okay. Point symmetry. This one's a little harder to see sometimes, but point symmetry. The best way of doing that is in parentheses. It says looks the same upside down. So if you can take the picture and go, and it look exactly the same, it has point symmetry. Okay, so point symmetry is sometimes a harder one to see. If a figure can be mapped onto itself by rotating it 180 degrees around a center point, and so, but the best way for me to explain it to you is to flip it upside down. Does it look exactly the same? The letter N upside down and right side up is the same. Capital letter N is. So it has point symmetry. Rotational symmetry is you can rotate less than 360 degrees and it be the same. Pinwheel is a good way to think about rotational symmetry. My male brain thinks about gears, and my son loves the little gear games, like little construction sets that have gears and stuff in them. So we do those a little bit, and he likes to turn the gears and see everything move and make it do things, all that stuff. But that rotational symmetry is if you rotate the gear just 5 degrees, or you may have to rotate it 10 degrees, but it makes it the same picture. That's what rotational symmetry is. So point symmetry is like rotational symmetry, but it's 180 degree rotation as opposed to different increments. Rotational symmetry is not a complete 180. It's different clicks along the way. That's the difference in the two. So what we're going to do, and I think one of the best ways of seeing this is just looking at some pictures and trying to decide what kind of symmetry they have. So it's a checkbox kind of game. We're going to look at the picture. We're going to decide, does it have line symmetry, point symmetry, or rotational symmetry, or it might have all 3, or it could have none of those. So the first picture, we got a hexagon shaped there. Could we draw at least one line in that picture and it be symmetric? Yeah, we could draw several lines of symmetry in the hexagon there. So we know we have line symmetry. And if we flip that hexagon upside down, does it look like the same hexagon? Yeah, so that's point symmetry. And if we take that hexagon and just click it roll it one step over, is it the same hexagon? Yeah, because all the sides are the same length. That's what makes that happen with this particular hexagon. So this one has line, point, and rotational symmetry, which is quite awesome. Now, number 2, we got a good old triangle. Fun little picture. What kind of symmetry could a triangle have? Line symmetry. Does it have point symmetry? No, definitely not. You turn the triangle upside down, it doesn't look like the same triangle anymore. So that's definitely not point symmetry. But could it be rotational? Yeah, so if we rotate this thing 60 degrees, it's going to be the, flop over on the other side, and we're back to being that triangle with the point at the top. So rotational and line on that one. Number 3 is a parallelogram. Does it have line symmetry, point symmetry, or rotational symmetry, or any of those? You can do a diagonal line. What are you suggesting? Because if you do diagonal from corner to corner, it definitely doesn't match up. And even if you draw a diagonal line here and fold it along that, they still don't match up perfectly because these angles aren't the same. Out of
So
that.
when you try to cut down to point symmetry, even though it switches to where it looks, it still.
It doesn't switch the way it is the same. It's the same. It's slanting to the right. It's slanting to the right. It's a sign. It does have point symmetry. That is correct. Rotational symmetry. What if I rotate it 180 degrees? That's point symmetry, but isn't point symmetry a special rotational symmetry? Rotational symmetry is anything less than 360 that we can rotate it and get it to match. 180 is less than 360. So that is point symmetry and rotational symmetry go together. If it's if it has point symmetry, guess what else it's going to have? Rotational symmetry. That doesn't go the other way, though. If you have rotational, that doesn't necessarily mean you have point symmetry. So, but if you have point symmetry, you automatically have rotational symmetry, is what happens there. What about number 4 there, that right triangle? None, because none of the sides are the same length, right? So if we rotate that around or flip that triangle over, it doesn't do any good. This one doesn't have any kind of symmetry to it, which is, I guess, probably more normal than symmetric. Number 5. Line symmetry, you could draw a line down I tried to draw it down the center there. That squiggly little line I drew there, that's the line symmetry, or a line symmetry. Does it have point? No, because it's got the point up at the top. When you turn it upside down, that point's now at the bottom, and it didn't have that to begin with. So it doesn't have point symmetry, but it does have rotational. If you just rotate it a click over and move this point up to the top, then it looks the same again. So it does have rotational and line. Crazy looking figure there, number 6. Point and rotational. Remember, if it has point, automatically has rotational. And it would not have line symmetry there. It doesn't match up even if you draw a diagonal. We want to think that if we drew that diagonal line right there, that it would match up, but it doesn't. It doesn't match up perfectly there, or really at all. Okay. The good old capital letter A. Line symmetry for sure. Does it have point? No, definitely not. Rotational. No. Lightning bolt for flash. None. It doesn't do anything there. No. You would be surprised how much that happens. Yeah. Yeah. Yeah, and they equate that with the A being a triangle type shape, and they think if you rotate it one over, it's going to do that. So that can happen. All right, number 9. That's a nice little shape. Some right triangles connected there at the vertex. Definitely point, because if you rotate that upside down, it looks the same. Rotational comes automatic with point. Does it have line symmetry? No, we want it to, but it doesn't. Number 10, kind of an hourglass type shape there. Line, point, and rotational. Good. Capital R. What's a pirate's favorite letter? You would think so, but they love the sea. That's a bad joke. Bad joke. All right, number 12. Line symmetry. Yeah, that's easy to see line symmetry. That's it. Good job. Good job. 13. I see airplane propeller. You may see the other things, but I see airplane. Say that again. Yeah, you can do a line symmetry. If you drew it straight down through that, like that, they would line up. They do a line symmetry. Rotational, but not point, because it's similar to a triangle, right? It's kind of the idea there. There's a company that has that in their logo, and I can't remember who it is. Maybe it's I don't remember. My brain is just saying that that's in a logo somewhere, and I can't. Maybe so. That may be what it is. I can't remember. And then 14, the letter Z. Point, and if it's point, it has to be rotational. Yeah, because you flip that Z over, it looks like a Z again. And fitting for the upcoming, I don't know if you call it a holiday. Some people do. Yeah, it gets all of them, line, point, and rotational out of that shape. And the Queen of Hearts, show me the line. Never mind. If I got to show it, I'm not telling. Just yeah, it won't fall. It won't work to do line because of the even if you did diagonally. Well, the picture inside of the card. Yeah, that one's a kind of a vague thing because it's got because we were been doing the shapes and we add pictures to it. It makes it crazy. Yeah. Yeah, the picture on that one would have to match up too.